So, dear students, welcome back in the second lecture. In the first lecture, we introduced splitting fields. So, now we are going to prove the theorem which guarantees the existence of the splitting field of a polynomial. So, we have theorem. So, theorem you can call it as the existence of splitting field. Existence existence of splitting field. Existence of splitting field. The statement for any field f, any field f, if f of x is a polynomial with coefficients in f, then there exists then then there exists an extension k, an extension k of f, which is a splitting field for f of x, which is a splitting field splitting field for this polynomial f of x. Now, let us look at the proof of this theorem. So, proof would be simple. So, proof, we have already given a hint of the existence part of a field which contains all the roots. So, we have a similar idea here. So, we first show that there is an extension, there is an extension E of f, E of f, over which the polynomial fx factors or splits completely into linear factors. Completely into linear factors. Into linear factors. And this we do by induction on the degree of this polynomial. By induction on n, which is degree of this polynomial fx. So we will show that there exists a field over which this polynomial fx factors completely into linear factors. Now, if the polynomial f is of degree 1, then we can choose the field E as f itself. So if fx is of degree 1, then it is itself a linear factor. So we can choose then we can choose E equals f, and we are through. Suppose now that n is n is greater than 1, the degree of the polynomial is greater than 1. We know by our previous knowledge, since f is a field, so this fx is a unique factorization domain. It is UFD. Means what? Means every non-zero non-constant can be expressed completely as a product of irreducibles. So this fx can be factored completely as a product of irreducibles. So what does it mean? It means that all the factors, no f is the polynomial fx is factored into the factors which are irreducibles. Again, if all the irreducible factors they are of degree 1, then we can choose E as f. Again, if all the irreducible factors are of degree 1, then we can choose E as f. Okay, we may take E as f itself. Okay, so otherwise at least one of the factors of fx is of degree 2. Otherwise at least one factor, say px of fx, is of degree 2. Degree 2. Degree at least 2. Okay. degree at least 2. Degree at least 2. So again, by the fundamental theorem of fields, there is an extension. So by fundamental theorem of fields, fundamental theorem of fields, there exists an extension, there exists an extension an extension E1 of f containing a root of px, containing a root of px. So this means what? This means, this implies our E1, the polynomial fx has the linear factor x minus alpha. The polynomial px and hence fx. So the polynomial, I will take px and hence fx, because any root of px is also a root of fx, and hence fx has a linear factor x minus alpha. Now the degree of the remaining factor, so the degree of the remaining factor, say f1x of fx is n minus 1, is n minus 1. So by induction there is an extension. So by induction there is an extension, there is an extension field, say E of E1, in which this polynomial f1x factors completely into linear factors, or this polynomial f1x has all the roots. f1x has all the roots. Now since alpha is in E1 and E1 is in E, so this means what? This means, so one root of this polynomial is alpha and the rest alpha, which is E1, which is in E1, but E1 is in E. So this means what? This means all the roots of the polynomial fx are in E. So E is an extension. E is an extension of f in which fx has all its roots, or you can say fx factors completely into linear factors, in which fx has all its roots, all its roots. Okay. So we are able to find an extension field of f containing all the roots of this polynomial fx. Now we have to ensure that it is the smallest extension of f. Now let k, so to ensure that it is the smallest, you take the intersection of all the subfields of E containing f in which fx factors completely into linear factors. That would be the splitting field. So let k be the intersection so k be the intersection so this intersection is non-empty because at least E is member of this intersection. With the intersection of all the subfields of E containing f. This is important. Containing f in which fx factors completely into linear factors, or you can say that in which fx has all its roots, has all its roots. Then clearly, then this k being the intersection would be the smallest. Okay, would be the smallest extension. So thus k is the splitting field for this polynomial. So the splitting field of a polynomial exists. Later on, we are going to prove that if there are two splitting fields, they are going to be isomorphic. So the splitting field of a polynomial would be unique. Now there is a barrier on the degree of extension of a splitting field. Okay. So before going to deal with this theorem, let me recall what we did in the example. In the first example, we chosen this polynomial x square minus 2 over 3. And we have seen that q root 2 is the splitting field of this polynomial. Okay, is the splitting field for this polynomial. And we know that the degree of extension of this q root 2, our q is 2. Okay, so 2 is also the degree of this polynomial. Okay, so there is a relationship between the degree of the polynomial and the degree of extension of the splitting field. Here they are same. Here they are same. And if you see the second example, we have chosen this polynomial x square minus 2, x square minus 3. And we have shown that this q square root 2 square root 3 is the splitting field. Is the splitting field. Splitting field. Again, if you see the degree of extension of this q root 2, root 3 over q, we know that it is 4. And again, this would be the degree of this polynomial. So we have a general result, in fact. So we have the theorem that we are going to prove. So we have a theorem. So theorem theorem So theorem says that a splitting field. So theorem says that a splitting field a splitting field of a polynomial of a polynomial of degree so a splitting field of a polynomial of degree n of of degree n of degree n of degree n over a field of degree n over a field f is of degree at most n factorial over f is of degree at most n factorial over f. So see the proof. So proof is proof so let fx is in fx and degree of fx is n. So let alpha be a root of this fx, then f1, which is f alpha, is of degree what? Is of degree at most n. At most n, we know this. I mean to say that this degree of this f1, which is f alpha, our f is less than or equal to n. And exactly n if and only if this polynomial fx is irreducible over f alpha. Okay, and exactly n and and n if and only if polynomial fx is irreducible. Now, this fx has at least one linear factor, one linear factor our f1, our f1, which is f alpha. So any other root of fx, so any other root of fx, other root of fx, say beta, satisfies a polynomial, satisfies a polynomial of degree at most n minus 1, of degree at most n minus 1 over f1, over f1. So this means what? This means what? The degree of extension of f beta over f1 is at most n minus 1, and it is exactly n minus 1 if the remaining factor of the polynomial is irreducible over f1. Now we know that the extension degrees are multiplicative. By using the multiplicativity of the extension degrees, using the multiplicativity of extension degrees, if E is the splitting field of fx, if E is the splitting field of this polynomial fx, then E is what actually we are reaching to this E by by finite number, in fact n steps. First we go to f1, then from f1 we go to f2, and so on, then we reach at fn. Okay, and we say that this fn is E. So then degree of extension of E over f by multiplicativity of the extension degrees, it is what? It is actually degree of extension of E over f n minus 1, and then E over fn, E over E I am taking, okay, and then fn over f n minus 1, and so on, f1 over f. So this would be 1, this would be 2, so on, n minus 1 and n, which is nothing but n factorial. So we are through. So a splitting field of a polynomial of degree n has degree at most n minus 1 factorial. So we stop this lecture here. So we will see you in the next lecture.